Let's talk about alternating polynomials. Okay, so we've been talking about symmetric polynomials until now, and this is sort of the same thing with signs plus minus. Okay, so let's define this. So definition: a polynomial f in n variables, f of x1, x2, xn, polynomial with integer coefficients, is said to be alternating as opposed to symmetric. So is said to be alternating if the following happens. Okay, so what's the condition? We permute the variables. So instead of x1, x2, xn, I write x sigma 1, x sigma 2, x sigma n, and when I do this, I don't necessarily get back f of x1, x2, xn, but I get that with a sign. Okay, so there's a plus minus sign here, and that sign is the sign of the permutation sigma, where epsilon sigma is the sign of sigma. Okay, and this is for all permutations sigma in Sn. Okay, so recall the sign of a permutation. For the even permutations, you have sign is +1. For the odd permutations, the sign is -1. Okay, so that's the definition. It's almost like the symmetric polynomials. So as a quick example, what does this mean? This just says that if I take, let's do this. So if I take example, if I permute any two of the variables, so if I keep everything else fixed, but I just interchange I and j, let's say. Okay, so what I've done is kept all the other variables fixed, not changing them, but all I've done is interchange the position of the ith and the jth variables. Now when I do this, that's a transposition sigma which has sign -1. So if I interchange any two of the variables, then I get back minus f of x. Okay, so that's actually an equivalent definition, if you wish, of what an alternating polynomial is. Okay, now you can see it's very close to the notion of symmetric polynomials. In particular, many of the statements we proved there will carry over to this case with slight changes, with the signs somehow put into place. So here's one of the statements we made there. Let f of x be the sum c alpha x alpha. This is the sum of monomials with some coefficients c alpha as being some coefficients. Now when is f alternating? Then f is an alternating polynomial if and only if the coefficients bear the following relation, that the coefficient of the multi-index alpha sigma 1, alpha sigma 2. So if I permute the multi-indices, the entries of the multi-index alpha, then this should give me, well, up to a sign. This is the sign of sigma times the coefficient c as sub alpha. Okay, and this should be true for all multi-indices alpha and for all permutations sigma and Sn. Okay, and the proof is more or less obvious. It's the same sort of proof we gave for the symmetric case. So just apply the definition. Okay, so I'm going to skip this. Now this so there's this notation which is sort of useful. So when I take a multi-index alpha, so let alpha be a multi-index and let sigma be a permutation, given these, sigma alpha will just denote the multi-index whose entries are what we wrote upstairs. You permute alpha like this: alpha sigma 1, alpha sigma 2, alpha sigma n. That new multi-index will be denoted as sigma alpha. Okay, so it's a nice shorthand because this appears so often. Okay, now observe a very quick fact from here. There are two facts really, just from the definition again. Number one, if alpha is a multi-index which has two parts which are the same. Okay, so if alpha is such that it's not distinct, okay, the entries are not distinct, is such that there exists ij with alpha I equals alpha j, okay, I not equal to j, two different indices which have the same value, then it's easy to see that means that this coefficient C alpha must be 0. Okay, so I fixed, so what am I doing here? I fixed an alternating polynomial. Okay, so let f be an alternating polynomial and let C alphas be the coefficients which appear. Then I am claiming that the coefficient C alpha is 0 if alpha is a multi-index in which some two components are equal. Okay, in other words, if alpha is not distinct, the entries are not all pairwise distinct, then C alpha is 0. Okay, why? Proof is very simple. All you have to do is just interchange, take the sigma which interchanges those two entries. Proof, let sigma just denote the transposition ij in Sn, the permutation which interchanges I with j, then observe the multi-index sigma alpha, so this is our new notation, is the same as the multi-index alpha. Okay, why is that? Because what's this multi-index sigma alpha? It's the same as the multi-index alpha, except alpha I and alpha j interchange places. But since they are actually equal to each other, what you get again is alpha. Okay, so sigma alpha is alpha. But then what does this tell you? But we already know this. The C of sigma alpha is epsilon sigma times C alpha, but epsilon is the sign of the transposition, which is minus. So on the one hand, C sigma alpha is minus C alpha, but on the other hand, C sigma alpha is C alpha because sigma alpha is alpha itself. Okay, this means that C alpha had better P of 0. Okay, so what this says is that the only alphas which appear in the support of f, okay, meaning when you expand f in terms of monomials, the only non-zero terms that you can have are the ones where the multi-indices that occur are all pairwise distinct. Okay, the components are all pairwise distinct. So that's fact 1, and now here's another fact. So I called it fact 1 upstairs. Yeah, fact 1, and here's fact 2, which is that the alternating polynomial is uniquely determined by its coefficients. So f alternating implies f is, I don't need to know all the coefficients C alphas. See, I already know that many of them must be 0, the ones where the multi-indices are not distinct. But this thing, if f is alternating, then it's enough to know f is uniquely determined by the coefficients, by its coefficients C alpha. So I should say by its coefficients C alpha for, not, I don't need to know it for all alpha, it's enough to know it for alpha being strictly decreasing multi-indices, for alpha strictly decreasing. For all alpha strictly decreasing multi-indices. Okay, what does that mean? Strictly decreasing just means okay. Again, why is this true? More or less obvious. Once more, we've already seen that C alpha is 0 unless, so proof of this fact, C alpha is not 0. Maybe let me call it beta instead of alpha. So suppose I have some term x power beta and its coefficient is C beta. That C beta is non-zero means that betas are all distinct, right? Beta 1, beta 2, beta n must be pairwise distinct. No two are equal to each other. So when I have a set of n distinct numbers, what I can do is this, I can arrange them in descending order. Okay, so let alpha be be the same as betas, let me call it beta i's arranged in descending order. So we had a similar notion when we talked about for the symmetric polynomial case, where we said you can look at weakly decreasing. In this case, it turns out to be strictly decreasing. So let alpha be the betas arranged in descending order. Then observe the constant C beta is just going to be, well, it's going to be plus or minus C alpha. Okay, and what is this plus minus sign going to be determined by? It's just a sign of the permutation that you need to use in order to rearrange it in descending order. Okay, so this is just going to be, this is just the sign of sigma, where sigma is what you need to rearrange alpha into beta or beta into alpha. So that sigma beta gives me alpha. Okay. So what does this say? This says, well, if I know the C alphas for alphas in descending order, then from that I can figure out what the constants are for all other terms C beta, where beta comprises n distinct numbers. And that's all I need, because all the other coefficients are definitely 0. Okay, good. So there is this weakly decreasing tuples of numbers which occurred when we talked about symmetric polynomials. And here what occurs is the set of strictly decreasing multi-indices. Okay, and it turns out they're actually both very closely related to each other. So let's write this down. So weakly decreasing, so I'll just use this downward arrow. So look at weakly decreasing n tuples in z plus power n, right? Weakly decreasing multi-indices versus strictly decreasing multi-indices. Okay, the left hand side is what occurs when we talked about symmetric polynomials. The right hand side is what occurs when we talked about alternating polynomials. And these two are actually closely related. There is a map, there is a bijective map, if you wish, which maps this to that. Okay, and what is that map? Let's describe it. So if I write an element here, if I take some beta, which is a weakly decreasing sequence, which means I take beta 1, beta 2, beta n, like this. So that's my beta. Now from that, how do I manufacture something which is strictly decreasing? Well, I do it as follows. I add to the smallest part, so to beta n, I will add, well, I'll add nothing. So beta goes to beta dash, where, how is beta dash formed? Beta dash is the following. I will take the n tuple as follows. So I take beta n, that's the last term of beta. To that I don't add anything. Okay, so I'm adding 0 to it. Then I take the one previous beta n minus 1 and I add 1 to it. Okay, I go beta n minus 2 and I add 2 to it, and so on. I keep going like this till I finally reach beta 1, right? So the very first term, and if you see how much I have to add to that, it will turn out to be n minus 1. So here's the prescription. You keep adding larger and larger numbers sequentially, 0, 1, 2, 3 and so on, starting from the smallest. Now when you do this, observe that what you get at the end must necessarily be all distinct numbers, right? Because even if originally they were not distinct, even if originally two of them were equal, right? Now what you have done is you have made them distinct by adding different numbers to each of the two parts, right? So even if, say, beta 2 and beta 3 were equal to each other, or let's say beta 1 and beta 2 were equal to each other, you have added n minus 2 to beta 2 and n minus 1 to beta 1. So the new parts are not going to be equal. Okay, so this is the map. Okay, and it's easy to check. It's actually a bijection. The converse map is also easy to describe. If I have a set of if I have an n tuple with all distinct numbers, strictly decreasing numbers, what I can do is I can subtract from those numbers larger and larger numbers. So for example, I subtract 0 from the very last term, subtract 1 from the next term, 2 from the next term, and so on till from the very first term I must subtract an n minus 1. Okay, so this map is a bijection. So the map beta going to beta prime defines a bijection between those two sets. Defines a bijection from the set of weakly decreasing n tuples to the strictly decreasing n tuples. Okay, and this has a very these numbers that I add 0, 1, 2, 3 till n minus 1, I can rephrase my map as follows. Let me define a special multi-index. Let's call it delta, which is basically these numbers, what I added, 0, 1, 2, 3 and so on, n minus 1, n minus 2. So that's my index. So this is again an element of z plus n. So the map that I've just defined for you, beta going to beta dash, can be, well, what is beta dash? It's just the new multi-index beta plus delta. Okay, and now plus is, I'm thinking of it like adding vectors. Okay, just component wise addition. So this is just component wise addition in z plus power n. Okay, so that defines a map from a bijection, and the one new thing, however, is that there's something to keep in mind, that the mod, meaning the sum of the parts, well, if you add up all the parts of beta plus delta, you will just get, it's all parts of beta plus all parts of delta, but the parts of delta are just 0, 1, 2, 3 till n minus 1. Okay, so that's the sum of the first n minus 1 numbers, so it's n into n minus 1 by 2. So this is a bijection, but the sum is not preserved. Okay, the sum adds in a very specified fashion. Okay, good. So that's the map here. Now, why are we doing all this? Well, because what we want to do next is to talk about some analog of the monomial symmetric polynomial. Okay, and this is what we call the alternate. Okay, what's the alternate? The picture to keep in mind is that this is it's a natural analog for alternating polynomials for the monomial symmetric function. It's the alternating analog, if you want, alternating analog of the monomial symmetric functions. Symmetric polynomials. Okay, so what is this alternating analog business? Just like how did we form the monomial symmetric function? We picked a certain monomial and then we symmetrized it in all possible ways, right? We took all possible ways of permuting the variables or the indices or the multi-indices, and that gave you the monomial symmetric polynomial. Now here we will do something similar, given there are signs that we need to take care of. That's the only thing. So given lambda in PDN, let's look at so given lambda in PDN, that's just a partition of D with at most n parts. So remember, we think of lambda as being exactly an n tuple by padding it with zeros at the end. Okay, so let's look at lambda plus delta. So consider lambda plus delta, I should say. Then given this, then lambda plus delta is, well, it's strictly decreasing, as we just saw. And so what we can do is the following. It's a strictly decreasing sequence. So let's form what we call the alternate indexed by lambda plus delta as follows. These n variables, it's just, so I start with the monomial x lambda plus delta. Now for the monomial symmetric function, what I would do is I will just take all possible permutations of this, right? This is the monomial symmetric function. Okay, but here I'm going to do the alternate, so which means I sort of have to take all possible permutations of the original monomial, but I'll take each of them with the corresponding sign. So this is now pluses and minuses. So this is the definition. A lambda plus delta is just you take x lambda plus delta, apply permutation sigma to it, but then you also put a epsilon sigma, the sign in front. Okay, now what's easy here is to see that this is alternating. Okay, so this is called the alternate. So this is the alternate. Indexed by lambda plus delta. Okay, so here's an example. Let's just take example lambda to be 1 1 1. So I'm taking, let's say, n equals 3 variables. Lambda is 1 plus 1 1 1. So what is lambda plus delta? Delta in this case will be 0 1 and 2. Okay, coming from the right. So it's 1. I add 1 to this and I add 2 to this. So this is lambda plus delta. So now what is the alternate corresponding to this guy lambda plus delta? x1, x2, x3. The definition we gave is the following. You start with the monomial 3 to 1 and now you take all its permutations. So first let me look at things where I only permute, keep one fixed and permute the other two. So x1, x2, x3, I keep this fixed, 2, 3, but then I must count it with the sign. Okay, similarly x1, x2, x3, I keep 2 fixed and I interchange 1 and 3. So these are transpositions. So the sign is negative. x1, x2, x3. I keep, sorry, what should I fix? 3 and I interchange 1 and 2. Okay, so these are the transpositions, and then I have to take the remaining two elements of the group S3, the symmetry group, which is the cyclic permutation. So I take x1, x2, x3 and then I cyclically permute the three variables, the three exponents, x1, x2, x3, and now I permute it in the left, 2, 1, 3. Okay, and now those are both even permutations, so I take it with pluses. So here's my definition of the alternate. Now observe, unlike in the case of the monomial symmetric functions, see there were cases, especially if this, because we took weakly decreasing, if two of the exponents are equal, okay, we had an example earlier, 4, 1, 1 as our lambda, then you may not get 6 terms when you expand. Okay, there we only got 3 terms, because there are only 3 really distinct permutations that you can form of the numbers 4, 1 and 1. But in this case, the exponents are always going to be distinct. Okay, and so when you permute, you will always get all 6 permutations. They will all give you different answers. So you will always get 6 terms when you do this. Okay, that's one point of difference. The other is that these have signs, whereas in the case of monomial symmetric functions, you only have all positives, all plus ones. Here you have plus 1 and minus 1. Okay, so that's an example of an alternate. And of course, here's the next lemma, which tells you that alternates perform the same role as monomial symmetric functions for the case of alternating polynomials. So lemma says let f be alternating. Then f of x1, x2, xn can be written as a linear combination of the alternants lambda plus delta. So plus n, where lambda is weakly decreasing. Okay, so observe I put lambda plus delta, so that's of course that's going to be strictly decreasing. Okay, so here's the statement that alternating polynomials can always be written for some coefficients c lambda plus delta coming from the set of integers. Okay, proof is, well, more or less the same proof that we have already given in the case of symmetric polynomials, but let me quickly repeat it. So you first take your alternating polynomial fx, you write it as a linear combination of the monomials x gamma. But what we know is that these coefficients have the following property: C gamma is 0 if gamma is not distinct, if the gamma i's are not distinct. Okay, gamma i's are not distinct. Gamma i's are not distinct. Okay, and in the case when gamma is distinct, you can get C of sigma gamma as some plus minus C of gamma. Okay, for gamma strictly decreasing, and for any permutation sigma. So these were the main properties. Okay, now what this allows you to do is to rewrite this expansion. So let's just go and write this again. So I now go back to my original fx, and instead of writing it as sum overall C gammas, I do the following. I pull out, instead of running over all multi-indices, I will only run over strictly decreasing multi-indices. So gamma strictly decreasing. And when I do this, what I get inside will be, what are the other possible multi-indices? The ones where these are some permutations of my gamma. But then I should also count it with an appropriate sign. So this is my fx, and this is just going to be therefore summation C gamma A gamma. Okay, because this term here is exactly my A gamma. Okay, and now of course we have seen this gamma is now strictly decreasing. You can replace it with lambda weakly decreasing, because we had a bijection where, okay, so I should have put the variable there of x. Okay, so it's the exact same proof that we gave in the case of symmetric polynomials. Okay, so that's the reason why these alternans are important. And so for those who sort of, at least for, if this expression seems to be somewhat familiar, so let's also make that connection here. You might have seen this before. So actually this alternant is in fact just it's a determinant in disguise. Okay, so let's just make this connection more explicit. So what's the connection with determinants? So recall, what's the alternate? So let me call it A gamma. Okay, so let gamma be strictly decreasing, gamma 1 greater than gamma 2, gamma n greater than or equal to 0. Okay, so I have a strictly decreasing n tuple, and I have the corresponding alternate A gamma. Now this is a sum over, okay, of x to the sigma gamma. Right, this is by definition. Now what's that? So epsilon sigma sine x1 to the gamma sigma 1, x2 by definition gamma sigma 2, and so on. Okay, and now recall that when you expand the determinant, this is the sort of term, this is the sort of expression you'll get. It's a sum over all permutations of the corresponding ijth element of the matrix. Okay, now what does this tell us? So it says that, okay, so if you form a matrix as follows, so recall, maybe let me also say this. So recall, suppose A is a matrix. Maybe we shouldn't call it A, let's call it something else. So suppose P is a matrix. Okay, then what's the determinant of P? Okay, it's some let's say K cross K matrix. Now how do you compute the determinant of P? You say, well, I run over all permutations sigma of sk epsilon sigma, and then I take P, I take the I take the first row, and in the first row I take the column sigma 1, the entry in that. The second row I take the entry in column sigma 2, and so on till P k sigma k. Right? This is what expanding a determinant means. Okay. Now let's compare this expression with the one that we have upstairs. It's almost matching. So I have the matrix that I'm going to construct. So I'm going to realize my alternate as a determinant of a matrix. The entries of my matrix must look like this. So this is the entry P, in the first row in the sigma 1th column is just x1 to the gamma sigma 1. Okay. So that should do the trick for me. So let's do this. So maybe let's define this matrix. So first let's take this k to be the same as n. So let's define the matrix P as follows. So what are going to be my entries? P such that the ijth entry of P is exactly xi to the gamma j. Okay, so if you define your matrix like this, the ijth entry is xi power gamma j. Okay, let's write this upstairs. Such that Pij then observe that this expression I wrote here is exactly going to match with this expression here. Okay, so I mean I'm assuming I'm talking about n cross n matrices here. It's the same n. So suppose I'm talking about n cross n matrices, then this will run over. All these are n's rather than k's. Okay, now it matches more exactly. So observe that I've got n terms, and then the entries are xi power gamma j. That's the ijth entry of the matrix. Then p1 sigma 1 will just be x1 power gamma sigma 1. Similarly, p2 sigma 2, this term here, will be x2 power gamma sigma 2. pn sigma n will give me xn power gamma sigma n. Okay, so what that tells me therefore is that observe that the alternate a gamma of x is nothing but a certain determinant in disguise. Okay, what is it the determinant of? It's the determinant of the following matrix whose ijth entry is xi power gamma j. Okay, ij running from 1 to n. So this is an important observation here, that it's actually just a determinant. Okay, and let's just do a very special case, which is, let's take gamma to be delta, the n minus 1, n minus 2, 1, 0 multi-index that we talked about. Then let's look at the corresponding alternate. So what's a delta of x? By definition, this is just the determinant of the matrix whose entries are xi power delta j, right? So xi power delta j. Okay, ij running from 1 to n. Now if you actually write this out in full, it will start to look a bit more familiar. This is the determinant of the following matrix. So what's the delta j? The last delta is 0. So the first row, for example, looks like x1 power n minus 1, x1 power n minus 2, x1 power 1, x1 power 0. Okay, x1 power 0 is of course just a 1. Okay, similarly the second row looks like x2 power the very same things, and so on. Okay, now this is exactly the famous van der Waals matrix. So the van der Waals determinant xn power n minus 2, xn power n minus 1. So the last row is just that.